for having me here. It's a great pleasure to be back, and I feel really honored and humbled to speak at this wonderful conference. So I'm gonna talk about counting with Wang tiles, and they'll come up later in the talk. So the way the talk is going to be organized, I'll have two parts. The first is going to be semi-philosophical, and I'll try to add some jokes to lighten the mood, but they might be lame. So don't expect too much. But there is no way to get around it. In order to understand the second part, I kind of need to explain the first part so you know what I'm doing at all. So one of the things I want to do is I want to start by praising something that may not need praising in this audience, what is now known as Online Encyclopedia of Integer Sequences, which has 250,000 sequences. And the quotes I chose may not be the most flattering quotes about these sequences and about this encyclopedia, but there's a reason for that. Basically, Neil Sloan says that we include only interesting sequences, but he never really says what are the interesting sequences. What does it mean for the sequence to be interesting? And as far as I can tell from browsing all the sequences, they're really all sequences. He just likes them all. And the second quote actually kind of underscores that. So Richard Guy reports that there are hard sequences, silly sequences, disallowed sequences. I tried to search for encyclopedia for disallowed sequences and didn't find any. I was mostly interested in those. I'll tell you what I'm truly interested as. I'm interested in the following two questions, which cannot possibly be answered, but I'll try. So what makes a sequence to be combinatorial, and what makes a combinatorial sequence to be nice? Okay, that's my goal. And I'll begin by showing you, that's the first edition, Handbook of Integer Sequences. The second was Encyclopedia of Integer Sequences. So the first one was published in 1973, for those who weren't born back then. Let me do the proving today. Okay. So if you look at this list of sequences, you'll notice some. So this is just from the first 100. I decided that you really don't want to see sequence 315 or 22,000 something. So some of these sequences are just trivial. So I guess you can figure out the formula for this one. That's a really easy sequence. If you think for a couple minutes, you can figure out for non-squares the precise formula. That's not too hard either. If you've ever taught undergraduate combinatorials, you can give a formula for the Fibonacci numbers. Some sequences are just awful. So this is a sequence of which orders numbers somehow alphabetically. So apparently 8 is alphabetically before 5. And so I'm not going to consider those. To those who've been staring at this New York City sign, so that's an A line. West 4th Street, at 116 is Columbia. I don't know, Port Authority is 42, and there are lots of streets in between, apparently. And there are lots more. So there are partition numbers, primes, etc. So one can argue that Fibonacci numbers, involutions, are truly great combinatorial objects. These are nice sequences. Some would quibble with when you count necklaces and graphs. This used to be considered combinatorial, but I think they are out of fashion now. These are unlabeled graphs. You really kind of don't want to count unlabeled graphs except asymptotically. And some sequences are just really, really hard, like number of finite groups of order n. So I'm going to try to explain what sequences I like. Okay? Which of these, etc. Can I go on? Everyone got all the jokes? Okay. So, such traditional answers to the questions I raised, and I mildly disagree with them and somewhat agree with them. So the sequence of combinatorial, if it counts combinatorial objects, that's not much of a controversy. Combinatorial sequence is nice if it's given by a nice formula. Yeah? We can all agree on that. The nicer formula, the nicer the sequence. Yes? Well, what else do you expect? And the final one is slightly perhaps more controversial. Nicer formulas can be efficiently computed. That's what people kind of expect from nice formulas. And this is all a little bit self-contradictory and somewhat wrong. So I'll give you my answers later. But first I'll give a long quote from Richard, who is somewhat struggling to explain what's a combinatorial formula. Can you see it? So I'll read just the first one. The most satisfactory form of f of n is a completely explicit closed formula involving well-known functions and free from summation symbols. So apparently, I guess as far as Richard is concerned, a formula something like 2 to the 1 over sine 1 over n factorial ceiling, that's fine. But summing that I from 1 to n times I, that's horrible. Well, so he is nodding his head. Yeah, okay. And he's saying basically he likes formulas, he doesn't like algorithms. That's my paraphrasing here. Now, at about the same time, a few years earlier, Herb Wilf wrote a beautiful, very short paper where he says, well, I have another definition of a formula. Formula is an algorithm, so he goes the opposite direction, which computes the sequence, but in time which is little o of the size of the sequence. Okay? That's a very clean answer, in contrast with this kind of vague. Of course, both are somewhat interesting and somewhat unsatisfactory. So let me argue first against the second one, which is truly awful if you think about it for 5 minutes. Let fn denotes the number of rooted labeled trees. So here are two formulas, according to Wilf, for the number of rooted labeled trees. So the first one is just explicit formula. The second one is n times the number of all labeled trees. And according to Wilf, that it takes this time to compute that formula, and that's little o of the total number, so it's a formula. Yeah. So the point is, the second definition maybe can be viewed as a quantitative, but it's really not qualitative. We would want to say what's a combinatorial formula and what's not. So Richard gives at least some affirmative answer, and this just doesn't seem right. Everyone good with this? Okay. Okay. So now I'm going to argue against everything. So let's in examples that we all know and like. So start with Fibonacci number. So we have so here are 3 formulas. Usually people think of the first as a definition, but I actually think of that as a formula. So the second one is actually a really nice summation formula, Richard. It might be 1+ in your book, I don't know, but it's really useful for various applications, gives connections to other fields, etc. And the third formula is just not useful for computation. It's useful for asymptotics, but how do you compute square root of 5? Well, if you think, like on a computer, calculators, graphical calculators can do that very quickly, but how to actually use it in a formal way? So that's already saying that what is a nice formula is complicated. Different formulas are useful for different things. I don't think that's very much of a controversial statement. Okay? More examples of stuff that doesn't work, of things we all like. So let's look at the derangement number. Usually when we teach, we say, okay, so there is this terrific formula, closest integer to n factorial over e. But if you actually want to give an algorithm for computing that, that's really not that nice. E is a really awful number. That, for those who don't know, it's irrational. So that already makes it rather unpleasant to work with in the usual computational models. So the second formula is really nice. It's actually explaining that formula, explaining it completely. I'm sorry, Richard, it has a summation sign. But it also has downside. It's alternating sign. So it's not a positive formula. So we don't like that. The third formula is actually the most efficient for computation. It kind of explains nothing. It's really, it's not even obvious how to prove that bijectively. You have to kind of think about it for a little bit. So it's the nicest formula computationally, but it's not all that nice to use for applications of derangement numbers. So one thing I want to note is that we really want a positive combinatorial formula in order to emphasize it's a combinatorial object. What? All of them are beautiful. But that's not the only criteria. Okay, so there is a problem whose name I cannot pronounce properly. So this is a problem of how to sit n couples along the table so they don't sit next to each other. And here are two answers to that number. One is this beautiful combinatorial formula, still non-positive, but quite nice, which was considered for decades, actually almost a century, the answer, the optimal solution to this problem. But I recently came across, this is just like Peter Pauli was telling us, so there are these YouTube videos of Doron Zalberger, and he has a long rant explaining that this is so much better than that. And he has his reasons, but it involves a lot of screaming. So let's move on. So basically, what I'm saying is, so here are my answers to this question. The sequence is combinatorial if it counts combinatorial objects. We're still good on that. So I'm saying that the objects are combinatorial. I want to actually specify what that means. If the fact that there's an object that you want can be verified efficiently by a nice algorithm. So combinatorial sequence is nice if the corresponding algorithm is nice. And my notion of efficient is corresponding algorithm is efficient, and my notion of efficient will be rather unusual, and that will involve tilings. But so basically, I'm saying that the algorithm will require only constant memory space. But so the way to think about it, once you have a tiling, it's really, really easy to verify that it's a tiling. You just look at each tile and check the boundary. Okay? And that requires a constant space. And that's what we're going to be doing. So let me be slightly more precise. So I'm going to want to find a finite set of Wang tiles. Again, I'll show you what the tiles are in a minute. So that nth number in a sequence is equal to the number of tilings of a rectangle, of an n rectangle. And as I said, verifying that it's a tiling is going to be really, really efficient. But the way from a general point of view, efficient here means that we're doing kind of computation with Wang tiles. It is. I'm not going to tell you. It's all the well-known studies of Wang tiles actually are extremely computationally powerful. You can do everything with Wang tiles, but somehow people never looked at counting with Wang tiles. And our counting is going to be on very special rectangles, and it's going to be slightly unusual from other things that people have done, not even close. Are we good on that? So that's the end of philosophy. I'm sorry it took so long. We're good on going to math? So tilings. So first I'm going to consider tilings of one by-n rectangle, and then I'm going to go with n by-n rectangle. What? Are you going to define one? Yes, that's what I'm doing right now. Okay, so here is the way to think of Fibonacci numbers. This is a way to tile a one by n rectangle with these three tiles. So these Wang tiles are just squares with colored sides. Since coloring sides is a little difficult to see from, so I just color this quarters of a square. Okay, and I want these things to match. So this is just like your favorite puzzle problem. The things have to fit, and it is completely obvious that the number of tilings of this Wang tilings of 1 by n region with this specific set of three tiles is a Fibonacci number, and the bijection is given by this example. So I put 1 if it's the leftmost tile, which is that blue, and somehow every time you have a tile with well, in my computer it's red, here it's maybe brown. With this one it goes with that one and vice versa. So these correspond to 2s. Okay, so it becomes a number of ways to write n as a sum of 1s and 2s, and that's one of the standard combinatorial interpretation of Fibonacci numbers. And Fibonacci numbers are one of those things. Once you know what you want to prove, you actually prove that very quickly by induction. Okay, everyone good with that? So, okay, so that's the definition of Wang tiles. That's what we're doing, and so more general. If you have a set of tiles T, and we're looking at a set of rectangles 1 by n, somehow I'm going to introduce here bookends. There's black colored boundary on the left and on the right, and I want to consider tilings of 1 by n rectangle, which begin with this black color and end with this black color. Okay? And the number of them is some number which depends on that. If you don't care, this is just a simple combinatorial setup, set of puzzle pieces, number of ways to assemble them. And now we look at these numbers a n of t, and it is an exercise on the transfer matrix method, very easy exercise, that the generating function is actually a rational generating function, classifying precisely all such sequences is possible and has been done. This is something which can be done via n rational functions, but I don't want to talk about this. That's the subject of a separate talk. What I want to say is that this is very small sequences. On the previous slides, we didn't have much of that, except for 1, 1, 1, 1, 1, 1. There is really not that many sequences that come out from this setup. Okay? But at least it's a classical setup. So that's what we're generalizing. Everyone good? You got quiet. Has it gotten too hard? Oh, no. Okay, maybe not. So here is my real problem. I'm going to look at the tilings of n by n square, and I'm going to prescribe these fixed boundary colors for each of the 4 boundaries, and I'm going to take a set of Wang tiles. Remember, I'm not allowed to rotate, reflect them, just parallel translation. And I want to consider all tilings of an n by n rectangle with copies of these tiles. Okay? And the number of them, a n of t, and that's what we want to understand. Okay? So just like on the previous slide, except you get many more sequences that way. So the questions that I want to solve is what kind of sequences I want to obtain, and the philosophical answer I want to give to the first part is I want to say that these are good sequences. These are nice combinatorial sequences. Okay? That's actually the right class of sequences to consider from my point of view. We good? Okay. So as a first test, kind of popular numbers called Catalan numbers, and so here's an illustration how I'm going to make them using Wang tiles. So I made a notation with so I have this tiles with 4 colors. So the 0 go above the dig path from lower left corner to upper right corner. The 2s go along the diagonal. The ones which are in blue are kind of in between the dig path and the diagonal, and everything below the diagonal is 3. And these are very different, types of Wang tiles. Okay? Yes. Here or earlier? Yes. I see you studied set theory. This is a combinatorial. That's a different story. Not to me. Okay, so thank you for your invaluable contribution to this talk. So that's not one of our sequences. Let's put it that way. So let me finish now the Catalan story. So basically what I'm saying is that I can essentially prescribe this using the colors, make sure that these 2s go along diagonal. That's the first thing I can do right away. And then I can prescribe that there is nothing other than 0s can be above and to the left of 0s, which will make it into a dig path. I can make sure that 0s are always above or to the left of 2s. I can make sure that anything is between 0s and 2s and 1s. These are all can be done by introducing a bunch of colors. Okay? It might take a little effort, but I can also make sure that anything that to the right of 2s have to be tiles of a certain kind. And I'm actually, this particular 3, for example, has to be slightly different from that 3 because it's in the corner. But I can make sure this all works. If I did the calculation, by the way, I forgot to say, everything is a joint work with my student Scott Garabrand. So we did a calculation, and we showed that this can be done exactly with 169 Wang tiles. But I think the intuition is clear here. It's really easy to using colors. It's really easy to enforce this kind of relation between tiles of different types. Yeah. Yeah. This is what I was saying before when I was greatly interrupted. So I fix a boundary, different for colors, but flat. So on the left it's color 1, on above it's color 2, etc. It's and it's fixed forever. And now for fixed, boundary colors, fixed set of tiles, it's a sequence, whatever it is. And I consider this family of sequences. So it's just like this formula here. An of t is the number of tilings, but n by n rectangle with these boundary conditions. So is the Catalan story clear? Yeah? Yes. Yes. I imagine it's possible. We did it this way, and we're not sorry. We really don't. How many tiles? Remember, it's not a quantitative thing; it's a qualitative thing. Either you can do it with Wang tiles, or you can't. If you can do, nice sequence. If you cannot do, not nice. Okay? Think of that as a definition. So I have a really long theorem. I don't expect you to read it all, and in fact, it's a portion of our theorem. So basically, we're saying that the meta theorem is that the definition is good. Everything that almost everything that you want, we already know how to do. So we know how to do Catalan numbers, integer partitions that appeared earlier, Motzkin numbers, really interesting sequence, number of Gestel walks of length n, number of alternating permutations, alternating sign matrices of size n, Baxter permutation. We can do a lot. This is just a sample of what we can do. And in fact, we have more general sequence which implies that, but I don't want to tell you. Yes? Yeah. So essentially we proved the more general theorems, which implies that we can prove that permutation of so here we have lattice Volkov different type, and there we have a general theorem that if you have fixed set of moves on a lattice, you can do them. Here we have a whole bunch of different results and permutations, and we have general tools to do that. So it's true, but it will still feel ad hoc, and these are more familiar sequences. So that's what we present. And so because I don't want to actually prove bigger theorems, I'll prove some of these results. Or at least, what was the way, Sasha, you told us? Convince everyone that we have a proof without actually giving anything. So this is what we're going to do. So if you want to pay attention to only one line, number 15 is really hard. That's the hardest sequence on the list, and I'll explain why later. That's the number of connected label graphs and vertices. Notice the difference between that and the total number of graphs and vertices. So we can do this one. We cannot do number of unlabeled graphs. And that's because it's a good sequence. The other one is not. But OK. So let me, in the remaining time, I'll try to convince you that we actually can do some of the sequences in this very constraining setup. So I'll try to guide you through these pictures. So this is how we represent permutations. Permutations have blue squares and whatever, yellowish squares over there. OK, I hope you see the colors in the back. And so there will be exactly one in each row and column. And to the left of each one, there will be above arrow going to the right. To the right of it will be above arrows going to the left. And you will always constrain the coloring on the boundary. You will always make sure kind of the relations that this in each row essentially starts with the row to the right or with 1. OK? We can always do that by arranging the boundaries, and same for the right one. And after 1, the direction has to change. So that's how we make sure that in every row and similarly in every column, we have exactly 1, 1. OK? So this clear? Essentially, that's how we do permutations. And we did a calculation again. We can do everything I said we can do with 405 Wang tiles for those who are counting. This is not to say we cannot do it with fewer, but it's just to show that even though this looks simple, in fact, there are actually quite a few possibilities for Wang tiles because of various ways they can be next to each other. You have to allow and not allow certain things. That explodes the number of tiles. OK? We're good with this? So for the alternating permutation, I didn't actually say what's the alternating permutation until now. Alternating, but we've heard the talks before about this. And these are permutation which increase and decrease and increase and decrease, etc. And so what I'm going to do is I'm going to introduce the asterisk that you see in even columns. OK? And essentially, I'm going to arrange my arrows. I'm going to make the restrictions that for after every asterisk, we cannot have one in the rows above that, because to the right of a blue square with an asterisk, there has to be a tile which goes with an arrow pointing down. And similarly, after every blue tile without an asterisk, there will be this yellowish tile with an asterisk which must go up, with an arrow must go up. And that ensures that this particular family of permutations that we consider is actually alternating. OK? This all sounds a little tedious, but how else are you going to prove that the number of alternating permutation is interesting or nice, depending on the adjectives that you want to use? OK? So again, if you're counting, we need about 146,000 Wang tiles to make sure this all works properly. But it doesn't matter. It's a constant. Yes. But it's because then you can get any sequence that are computable, and this has a very restricted setup. Essentially, I don't allow. The computation we're doing is extremely constrained in a certain sense. But the notion of emulate is a complicated notion. What does that mean? So you can is your input a region or what? And it's actually, in fact, it's kind of interesting. In the very first paper on NP completeness, Levin's so this P versus NP was introduced by Cook and independently by Levin. And Levin actually, one of the problems he discussed in that paper was about tilings. These particular tilings, Wang tilings. So he knew back then that yes, tellability with Wang tiles is NP complete, but there the region actually is part of the input. You see? So even so, for a fixed set of tiles, when the input is a part of the input, that's a hard problem. What we're doing is very, very different from computational point of view. There's a very low complexity model of computation. Yes. That's already different, but in fact, it's different in many more ways. We really don't have our input is n. So our boundary coloring is also fixed. So n is a very small input compared to 3-sat formulas or other kind of formulas that you can have as an input. You really cannot embed too much into n. Okay, let me do quickly or relatively quickly Baxter permutations. Baxter permutations are unusual and interesting. So for those who've never seen them, here is the definition. It's a certain kind of pattern avoidance, very specific, that was introduced by a couple of Baxters some years ago. So what is key to our, so somehow because of the way this definition is structured, it's actually not very easy to see that one can find such a set of tiles, and it has to do with the structure of Baxter permutation. Essentially, we're saying that on top of this, whatever it was, roughly 400 tiles which define a permutation, we add lots of layers so we create a lot more tiles in a way which would prohibit a certain 2 by 2 matrix. This is just one of them. So I'm basically saying that this permutation is not Baxter because it has that submatrix. That's a property that's not a general property for all pattern avoiding permutations. That's a property of Baxter permutation, that they have this. Well, it follows almost immediately from definition that it has these 2 adjacent rows, and in this adjacent row you can find this 2 by 2 rectangle which works that way. Okay, so somehow what we're doing now is we're saying, okay, so I'm going to introduce a lot more tile pieces to account for various possible arrangement of 2 by 2 square, and I'm going to make sure that the colors are chosen in such a way which would prohibit this specific 2 by 2 submatrix there. And I can do that by exploding the number of tile pieces, but it's okay. It's still finite. Okay? So we cannot, I'm not saying we can do all pattern avoiding permutations. So if you have a random color of length, a random pattern of length 10, I cannot prove that it's interesting. But I can prove that this particular is interesting. You see? So I don't expect you to actually follow what is this 2 by 2 matrix. That's getting us slightly off track. But I do expect you to see that there's a general pattern here. So this is an example of a somewhat different kind. Here I'm considering set partitions. So in this case, set partition 1 to 5, 3, 6, and 4 So these are columns 1, 2, 5, 3, 6, 4. Can you see that? And now I'm saying that I'm going to find basically I'm doing a kind of trivial bijection between set partitions and arrangements of these blue-colored ones in this n by n square. Okay, so I have this trivial bijection, and now I'm saying that by introducing these arrows, which have to go to the left like that in ones, there is only one blue color which in each row which does not have an arrow. See, the leftmost doesn't have an arrow, and I make sure that the arrows go from right to left and then stop, and there are no more arrows to the left of ones, and whatever is below ones have to have an arrow pointing up, and whatever is above ones have to have an arrow pointing down, and these are conditions just like we've seen for the permutations. Okay. So my point is by introducing this type of bijection and making various constraints on the way Wang tiles can be next to each other, I can make sure that that the total number of tilings is the number of set partitions of an n set, and that's what I really want. So that's again saying that my computational model is powerful enough to compute that sequence. Okay? All right, so let's go for a bigger price. So this is, so now I'm computing integer partitions. And let's see. Yeah, let me tell you roughly how to do it, and then I'll tell you maybe a little bit answer your question about general theorems. So integer partitions I'm going to do, so I'm going to have arrange partition 4, 4, 2, 2, 1, 1, 4 square, 2 square, 2 square, 1 square, 1 square in blue. And I'm going to make sure that everything above is yellowish and everything below is slightly different shade, yellowish. But essentially, it's pretty easy to make sure that these blue things become common squares. That's the routine things to do. What's non-trivial is how do you make sure that that the size of this square is bigger than the size of that square? That's slightly non-trivial. And the way I do it is I make sure that right below the lower left corner of each square, there is I don't know if you see the difference in shading. Do you see the difference in shading? There is like a diagonal going on here. And I want to make sure that no blue square goes below those diagonal, or no below that diagonal. And that's very easy to arrange, again, with these colors. And so right below lower left corner of each square, there is a diagonal going to the right. And this diagonal must not be, so these diagonals must be defined, and so they cannot have blue squares. And that's how I do the whole thing. If you look carefully at what I'm doing, you can actually see that, in fact, even though I painted this all blue, the upper left corner, lower right corner, lower left corner, upper corner, very different tile pieces, very different tile pieces. And the ones in the middle here are kind of all different, and in the middle here are different again. And this is all can be arranged to make sure that this is a square. Yeah. Yes, that's what I'm doing the whole time. If it's a permutation, I have 400 whatever 5 tiles which give you n factorial. If it's a partitions, I want to make sure. I forgot what it is, but it's in hundreds of thousands of Wang tiles that I need for the. No. There exists a set of tiles T. So that for every n, this is the number of partitions of size n. Yeah. I don't know what you said, but what I said is right. So I'm looking for a set of tiles T, so that for every n, number of tilings of n by n squared with set of tiles is the sequence that you want. In this case, number of partitions of n. Okay, good. Yeah, actually, about 10, yeah. But that's kind of not true either, because on the lower left corner has to be, it can be the boundary, it can be right above this diagonal thing. So there is more involved. That's actually quite a bit. So in total, you need several hundred thousands. I don't remember how many. It's our upper bound. It's not meant to be tight, but there is somehow I'm being fast and vague because I don't want to be slow and careful, because then I wouldn't be able to explain even single one of them. Okay? Yeah.
Just a follow-up question. So, for instance, you had a 5 by 5 or 6 by 6 rather than 4 by 4. Schematically, it would look very similar. It's corner, it's a middle, so you have like 3 4s in a row.
Again, so I'm defining your set of tiles. I'm defining it using a picture, and then I'm saying that for that square, whatever it is, it's like 10 by 10. The number of tilings with that giant set of tiles is going to be number of partition. But because the number of tiles that I need is so huge, I can't actually possibly draw them on a blackboard. They're not going to fit. So schematically, basically, I'm saying that with the same kind of color and letter, I'm actually encoding a lot of different tiles, so that for whatever tile you have, they will have this schematic shading. But there are many more tiles actually happening here. Did I answer your question? No. I see. Okay. So if you have, this is analog of 4 by 4. So essentially, I'm going to have different kind of blue, whether there's the corner or on the side or in the middle. That's what I was saying. So 4 by 4 is to show that you can have the middle. Yeah. This is okay. So these are all basically the same, but on the boundary, because of the way it interacts with the rest of the computation, you actually have lots of different kind of those. But if you ignore the difference, they're all the same. Okay, still true. So this is the harder one, and I really don't have time to explain anything about that. So this is a whole bunch of pages. So I'm saying that if I want to compute number of connected graphs on n+1 vertices, the asymptotics is already huge. Basically, almost all graphs are connected. Okay, almost all labeled graphs. So if you have an n by n square, this number barely fits inside. Okay, you really cannot do much of a computation here because there is no space. How do you make tiles interact with each other to make sure? How do you embed graphs into that, into this tiny space of n by n? And the way we do it, we ignore the graphs completely. We use a rather standard, at least I think it should be standard, recurrence relation for this number. And then we essentially show, just like with the partitions, remember with the partition, we split things into a bunch of blue things. Here we also split things into smaller numbers of connected graphs, but you have to do it very carefully because you really don't have much space to go on. So that's what makes this problem really difficult, and we need tens of millions of tiles for that. So I have just a couple minutes left, so let me tell you one kind of theorem that we can do. one kind of theorem. I'm not going to write it, but essentially the result, so if you follow the kind of standard ideas from theoretical computer science, you can prove the following result. If you can calculate the sequence in linear time, then you can do it. Then you can do it in this computational model as a number of tilings of a square. The problem is that such sequences basically don't exist. There are very few sequences that are computed in linear time. For example, if the sequence grows exponentially, writing that sequence takes linear time. Okay? And so, for example, you cannot compute Fibonacci numbers in linear time. I'm sorry. Even though you would think there are these beautiful formulas I showed to you. No, that's not how it works. The more interesting example is this example with the partition numbers. I looked at all possible literature. If you, partition numbers grow sub-exponentially. It's roughly e to the square root of n. So how can you compute them, these numbers p of n in linear time? No one knows, basically. So the standard recurrence relation using pentagonal theorem uses square root of n terms. That's the first thing already. You have to, it uses square root of n digits. That's already n. But you have to do it n times to reach p of n. So that's n squared. For those of you, give me a second. For those of you who know too much and know there is this Hardy-Ramanujan-Rademacher formula, try to implement this in this model. It's not going to work. So I doubt that you can do that. You can actually compute this number of p of n in linear time. But this is not the kind of results that computer scientists can prove. They usually are good at upper bounds, not the lower bounds. Another thing. Let me see. So we have a slight generalization of that. We have a slight generalization of that theorem that I mentioned. So suppose there is a computation which has time times space, big O of n squared. So that's a little larger set of algorithm, and then you can using a lot more work, we can actually implement that computation in this n by n square. And we thought I should explain that until, again, I went through a long list of sequences and realized that there is only really one sequence. Let's call it f of n. This is a number of partitions into powers of 2. So if you look at number of partitions into powers of 2, that number grows roughly like n to the log n, and you can actually calculate it in linear time and slightly superlinear time and roughly logarithmic space, and that allows you polylogarithmic space, and that allows you to apply our general theorem to prove that this sequence is done in our framework. Unfortunately or fortunately, by using our tools and our other general results that all kinds of partition families can be done, we can just do it directly. We don't need this powerful theorem. So somehow these theorems are very weak, very hard to prove, and there are very few sequences to which they can be applied that we cannot do directly. So that's why I'm not telling you any of them. Okay, that's it. Thank you.
Questions for Igor?
Is there any benefit to shrinking the number of tiles that you need in order to compute a sequence?
I don't see any. Essentially, I'm trying to say that some sequences are good and some sequences are bad. And they're not better than just because you need fewer tiles.
Okay.
It's in contrast with what Wilf is saying. This is not about time complexity of computing them. And moreover, if you think about it, the way we speak of combinatorial sequences, we really don't care if we can compute it fast or slow. When we speak of the number of partitions, so for example, number of partitions into ones and twos of n, into partitions into part sizes 1 or 2, that's very easy to compute. And semantically, it's the same as the total number of partitions. So we would consider both to be nice. But one number is much, much larger than another number, you see. And one is much more efficient to implement and so forth. So I'm essentially saying which sequences are good or not, and I'm creating the whole, this whole talk about that.
So I'm invading from probability, so correct me if I'm wrong. It is not O1 memory to check that a graph is connected, correct?
Yeah, but that's not what we're doing.
Right. So does what you're doing, is there a bijection that I could then use in a roundabout way to get an O1 way to check that a graph is connected?
I see.
Or are connected graphs just not the combinatorially useful?
That's actually what you said. Let me explain. So checking that the graph is connected is almost linear, but slightly, inverse Ackermann function, nonlinear kind of thing. So I'm not making a bijection. I'm not making a bijection between connected graphs and these tilings, because I'm just computing a sequence, not making a bijection. One can make a bijection, but implementing that bijection would require superlinear time. Okay? So all I'm doing is saying not which combinatorial objects are good or bad, but which sequences are good or bad, and I'm computing the sequence. So it's a small distinction, but important. Sorry, I don't know. It's your job to point.
I was going to ask how this compares to like recognizing the objects on with a cellular automaton, but I think what you just
very connected. Essentially, you remember you remember that model. That is equivalent to the model that you're talking about. If you're doing recognizable languages, they're in one-to-one correspondence with this Wang tiling. That's the same thing. If you write instead of alphabet, you write Wang tiles in line. So essentially, this idea of studying them goes back to Klinishitz and Berger, etc. There's a long history that I'm not writing.
Do you have an example of a bad sequence?
I wish. We do have an example. If you like a trivial example, if you want to calculate 2 to the n cubed, that's not going to work. There's just not enough space in your for that number of tilings. We have a kind of a conjecture. We think 2n choose n to the n, that kind of sequence, it fits. It fits in asymptotically, potentially, just a little bit below 2 to the n squared. But we don't think we can compute it using this set of tiles, and that's nice enough already. But remember I said in the beginning, number of non-isomorphic graphs on n vertices. Checking graph isomorph is really hard. Embedding graphs is really hard. There is no way to do that, but there is no way we can prove that either.
My question got stolen.
Okay.
Say your things you're trying to count come along with some nice weight function, like the length of a permutation or something. Is it guaranteed that if you can do this, you can then assign weights to the tiles so that you can produce the generating function?
No. Not really. We really, it's hard enough to do in this model to obtain a precise form generating function. Basically, you have to look at the graph on all possible tile pieces and do the transfer matrix. For the n by n, this is a famous problem. Look at number of domino tilings of n by n squared. That's a really tiny special case of what we're doing. Try to count them precisely. That's already very hard. So in my greater generality, hopeless.
So do you plan to consider like higher dimensional tilings, like 3 and 4? That would probably make you more inclusive. right? It's for which sequences are good.
Yeah, but so if you do three-dimensional, you can do that. We plan to publish this, not consider more. We have a limited time goal.
Maybe in the same vein, hexagonal tilings or other shapes. Can you maybe prove that? Are those equivalent to?
Yeah. It's not so bad.
What if it's not simply connected?
No. This is n by n squared. Not simply connected doesn't, then the boundary has to be an input. We don't want to consider those. Oh, you're thinking
Do you
like,
think you would get other sequences if you did that?
like if you do that, I don't know.
Yeah, I know it's some fixed.
I doubt that, but
Your loss of time
I haven't thought about it. This
Yeah.
is somehow I didn't emphasize enough, but in kind of tiling community, bank tiles are the foundational kind of type of tiles. Yeah, so everything people do is with bank tiles. I can't think of the top of my head what would be analog in other parts of. So it's like Catalan numbers for sequences. Let's put it that way. So there's the main one, and we wanted to deal with them just because they're natural and everyone else does work with them. So they were used to prove that there exists a finite set of Wang tiles which will have a tiling of the plane but not a periodic tiling. So these are famous results that I kind of alluded to in the beginning with my picture here on
So
the
this
right.
is related to Penrose?
Yeah. Yeah. Penrose is a case with two tiles, but they're not Wang tiles. The smallest set of Wang tiles is like 13 or something. There is a finite set of Wang tiles which can do that.
So I know you said you don't care about the number of Wang tiles, but if you go from like 1, 2, 3, and so on, and you look for all the sequences you can get with that many tiles, at some point you will find one which is not in the list.
On which
Or-
list? Oh, on
Yeah.
$250,000 list, I'm sure, yeah.
So-
But remember, Sloan doesn't want to consider just random sequence. He wants interesting sequences. So I don't know if you want to look at the
Yeah, but-
17 set of 17 Wang tiles with 112 different boundary colors and say, okay, that's interesting enough to be included. And I checked, for example, it has Fibonacci numbers, Fibonacci numbers, Fibonacci numbers, but not like 10 Fibonacci numbers. He has a breaking point at some point.
Yeah. So once you find it, because I didn't finish my question, once you find it, now it's your job to make it interesting, right?
Yeah,
to find an underlying.
that was my job. But so.
All right, thank you again.
Thank you.